Hi everyone, in this tutorial we will create a Mandelbrot set, which is a special type of fractals. So what are the fractals? Well, initially fractals are based on complex numbers, and the nature of fractals is in the recursive function. So let's see what does Wikipedia say. Mandelbrot said. So here's our function. Z and C are both the complex numbers. So it is possible to go with a straight formulas and complex numbers, but I found this more interesting to go with a vector math, which will give the same result for sure. So to do a Mandelbrot set with a vector math, we have to follow a few steps described at this page, skytopia.com, fractal Mandelbrot. So let's see. Okay. So this guy is telling us that we do not have to know anything about complex numbers, but we can go with vectors. So first of all, we have arbitrary point in space. This is Cartesian space. So this is our vector, because this position is a vector itself. Step 1. We need to rotate this vector around the center with the same amount of degree. So just double the degree. So we have this point. Then we just multiply this vector by itself, by this module. This is square. And the final step, we're adding the resultant vector. We're adding both vectors, the resultant one and the initial, with this one. So finally we just iterate the process. We just do this over and over again. And the rule is, if this point is going to the infinity, so it doesn't belong to the Mandelbrot set, and vice versa. Okay, so let's do this from scratch. Particle systems, thinking. Okay. Properties. Oops. Let's create a group. Call this 2D Mandelbrot. So let's back to our steps. So we have a point. Okay, let's do this with a simple particle, just one. Mandelbrot. Create another group. Call this origin. Master dynamic. Create Mandelbrot. Let's call this 2D Mandelbrot. So since we will be testing all these steps with a single particle, so let's call this, I don't know, maybe 2D tester. So, and then create another one inside of it, and I'll call this create maybe origin. So let's start with a point, and the point, create this one, display as box, side of maybe 2.001. Okay. Operators generate a position born. Then we create a node, standard node. So we're creating the particle in the exact position of this point. So we have a node, pick a node, our point, position, connect this, pistol shot 1, and the group should be origin. Okay, let's see. Yeah. So here we have a particle. Oops. Turn off the speed, I believe. Lifespan. Size. Speed is 0. Yeah. By the way, turn off edit on fly. Let's see this as tick origin. So actually, let's start with not a first frame, oops, but frame number 1. Okay, so the last time length, okay, and time is 1. Let's color that as red. So if you move our point, so okay, it does work. So to go ahead, we need to feed this whole process or cycle. So with starting parameters, which are this angle, this is 63 degrees at start. So the initial length of this vector on this position, let's call this radius, and the initial position. So we can do this with the memory node. Let's see. To the Mandelbrot. Well, actually, let's call this just Mandelbrot, right? Okay. To the tester. Operators, standard, memory. So we can create alpha. This is a scalar. So then we create radius, which is scalar also, and the initial position, which is vector. Init pose. So the vector, okay. Memory, let's go ahead. Create origin. So we need to know an alpha. So top view, this one, this angle, we have to know this. So how do we do this? Let's go, okay. Operator standard, particle data. Oops, no. Helper standard. So particle data. connect that. Helpers, math, 0.3. Okay, so now we feed up 0.3 with the position of Bohr particle. So by the way, this is not really necessary to do this. You can do it right. So, but 0.3. Okay. So how to know an alpha? Let's see. Our space is x and y. Here's our point. This point has an x component of that position and y. So if we divide y by x and call the function called arctangent, so we will know this alpha, which is our angle. Okay? So let's divide x and y. Math, multiply, division, y, divide by z. So, and then we call the function, okay, 8, 10. Beautiful. Helpers, math. Oh, where is that? Math. Input is float. Known. Arcus, tangent, tangents. Okay. So let's call the memory again. Very standard memory. Alpha input. Let's see what's happening with the debug. Let's see. Oops. Here's our debug. Point 5, 0.6. Arcus tangents. So this is in radians, I believe. So let's make sure it does work. So 0, 0. Duplicate that. Copy. Let's display that as cross and link that. So 1 radian in degrees, I believe this is 57. Okay, so 40, 46, 51, 57 means something like 1. Yeah, it does work. That's okay. Okay, cool. So the next step is we need to feed this with the radius. Here we are, and the radius. So we can do this with the math also. Helpers, math. Float input, we have to feed this with a vector and output the length. Depth R. Okay. Let's try this also. So the position will be, oh, that should 7, 7, 8, 3. Okay, it does work. Good. And the initial position, which is the position itself. let's call this. Okay, so we have created the origin point. Now we know the angle, we know its length, and the initial position at the start, which is really important because at step 3 we're adding this initial position. So this is a vector, and it is a constant vector through the whole process. Okay, good. So far we have initial position, radius, which is the length, and alpha, which is an angle. So we need to follow, we need to repeat step 1. Step 1 is rotation, rotation of point. So we double this angle. Okay, so how do we do this? Let's create a new dynamic set and call this create trace. We have to call our memory, pretty standard memory alpha in output, radius, and initial position. Okay, so alpha. How to double this? Simple. Operators math float. So just feed this in and say multiply this by 2. And let's call this like alpha. Oh, well, 2 alpha. Okay, multiply. Oh, here's the math. So here's our initial point, which is, let's call this our vector, which has a module. So we need to know, let's say x0, y0. We need to know x1 and y1 after this double rotation, right? So the rule is x1 equals module r, we already have this, which is length, multiply by cosine of 2 alpha, and y equals r, or this vector, I'm sorry, multiply by sine of 2 alpha. So we have 2 alpha. For sure we need to have a math helper. Okay, feed this in, which is float, and call the cosine function. Cosine theta. Let's rename this cosine 2 alpha. So, like I said before, x1 new x r multiplied by cosine 2 alpha. helpers math add multiply. R and R cosine 2 alpha. Let's rename this new, let's say x, maybe 2D. Same for y. Let's duplicate this. Plot, which means to alpha. Not the cosine, but the sine. Oops. Sine to alpha. Sine to alpha. New x. New y to d. Yeah, this is good. And multiply by r. Oops, I'm sorry. Multiplication. It have to be a multiplication. It has to be. So currently we have the two components of our position, which is vectors. So we need to feed this into 0.3 helper math at a 0.3. Oops. Okay, that's x. This is y, right? And it, okay. So let's test this also and create another group. Let's call this, not to code, just color code this. Let's call this trace, right? So we need to born another particle with this position. Operators, generator, and position born. Vector, position, trace, pistol shot. Let's do this. Well, per call. Okay. So as we can see, let's rotate the parent dummy. This new particle is exactly at the position that was before, but with the double angle, which is good. It does work. So this is good. Okay, so let's call this trace. So our step one. So we have done step one. So we multiply this angle by 2. So we're going right direction. So okay, this helper is standard command. This will be step 1. Let's go ahead. Step 2. Step 2 is a multiplication, this new vector by itself, by the module. So we can do this with the math operator as well. So let's create the math helper math. So at the input we have the vector. So, and then we have a float. This is important thing. Is called in new TP. I don't remember which version is it. The data flow conversion. The data flow conversion is tends to be so. If your output vector to the float, this will output the module of this vector. So, which is really convenient. So we have to multiply this by itself, so we choose multiplication, vector, and the float, right? So let's test the next step, position, and so what do we have? So let's do this 0 and rotate this. Oh, as you can see, if our module or radius is larger than 1, so this new position tends to fly away. Let's see. 0.447. Let's do the same. Oh, which is smaller. Let's do this smaller. 447. 0 and x is 447. Right? And we'll rotate this. Have to be something like here. Looks like a truth. Let's reduce this. Okay. So 0.447. Oops, sorry. So I forgot to zero the speed. Sorry for that. So for sure it does work. So 90, 180. Good. So here is the step. Oh, step 2, right? This is step 2. Let's copy that. Rename this step 2. So our step 3 is adding the initial vector to the new position. Let's do this. Duplicate the math. So both our inputs are vectors. So we have our new vector from step 2 and the initial position, right? So let's try this. Yeah. So our input 447. 447. Rotate this. Oops, this. So it seems like we go in the right direction, right? So all the steps done. So this is step 3. Step 3. So as you can see, we have the new position, new vector, so which is the position, and the new alpha, right? This is our vector, and this is our alpha. So we rotated this and multiply by itself, and added a new, no, I'm sorry, not new, but the initial vector. So to cycle the process, we need to feed all our parameters like R and alpha. So let's do this. Disconnect that. So parameter standard and the memory, alpha, input, and R, which is scalar. So so we can just copy that, multiply, so okay. So let's rename this. This is our create origin, and multiply, rename y divided by x, rename r, and this is alpha. So just copy that, paste it. Math vector. Also, obviously we need the 0.3 helper node. So let's copy that also. Copy and paste. So we have vector with new position, vector y divided by x. Okay, this vector, which is new length. This is alpha. Yeah, this is right. Okay. So in R, by the way, let's try to save this. So I believe this will work each frame. So let's try it. Oh, doesn't work at all. I apologize. So I just forgot to connect this position with this vector. Let's see what's happens. Let's see what's happening. And 1. We're starting with first frame. 2, 3, 4, 5, 6. So as you can see, each frame, it calculates the new position, new alpha, and the new radius. Okay, so it's taking from the memory. We're starting with the initial position. Oh, I'm sorry, create origin. Feeding up, and go ahead. So double alpha, multiply by itself. Step 2, and add in the initial vector. Step 3. So and then for a new point, this is our new point. Again, we are calculating the radius, the length, and alpha. Okay, and then we started to do this over and over again, but with the frames, which is not really good because we need to do this with one frame. So how to do that? We can use iterator. So 6601. Let's bring this back. Helpers, operators, initiator, iterator. So we can do this operation, let's say 10 times with one single frame. Turn this on and let's see, right? Also can add the condition standard time interval from 0.1, I'm sorry, frame 1 to frame 1, just once. Okay, so let's rotate this back. What's the point of this all? And the point is, let's bring this back. We can see what the particle is doing. Is it flying away, or it tends to be closer to 0 point? So, as I said before, we could do this with the complex numbers, I'm sorry. But with the vectors, we see what's happening, and this is really good, in my opinion. So we have a point, which is the red one, and it's starting to rotate, multiply by itself, and add in the initial position. So, and we see the track. So for this point, I believe this point will be in Mandelbrot set. And this point, this initial point, wouldn't. Okay? So because it flies away, as you can see. So let's try 100. See? So it's going away really fast, so we don't see 100 at all. So the conclusion of this tester is we're really sure that we're going the right way. So the next step will be the building on all the Mandelbrot setup, but not with one point, not with a single point, but with a two-dimensional array of this. Okay, so far we have examined a single point, as you can see. So whether it does escape or not. So we're sure that we're going the right direction. So let's see it again. So those steps were built for a single point, but we have to check every arbitrary point and do this for each and every point of this process, and we have to make this. For sure, we need to build an array, a two-dimensional array of those points. Okay, so let's do this. let's create another dynamic set and call this, oops, this will be our 2D Mandelbrot. Okay, so as you can see, this Mandelbrot set is bounded into some coordinates. So 1 and minus 2 are critical, and minus 0.5 and minus 0.5, 1.5 is critical also. So we have to build points in this square. Okay, so we can start with, I don't know, maybe helper math float. Let's call this rename x1, duplicate this y1. Okay, so we're creating a vector, helper math 0.3. Let's try this, x and y. Okay, so let's call this v1. This will represent the critical point, which is right in top direction. So this will be 1.5 and 1. X is, oops, I'm sorry, 1. Y is 1.5. Okay, so this will be 1, 1.5. Yeah, good. So we have one vector, this one. Just let's create another one. This will be minus 2 minus, let's say, 1.5 also, because this is symmetrical. Okay, v2, let's rename this x2 and y2. So once again, x minus 2 minus 2, y is minus 1.5. Good. So now we have to know the total length between x1 and x2 and y2 and y1. So to know this length and this one. Okay, so this will be math and multiply. Let's call this delta x and call this one delta y. Spit out these values, x, oops, y, x, x, and y. So since it is delta, so we have to minus, I have the minus set. Okay, so it has to be x1 minus x2 and y1 minus 1, 2 minus y2. Okay, so now we know the total length of this and this one, and the point is we want to divide x and y portion, but the same amount of but not the same amount of particles. This wouldn't be the same, but with the same distance between them. Okay, so we will use some parameter called raster. Let's try this. Okay, helpers math float. Let's call this raster. Okay, so let's do another float. Call this float. This will be 1. Let's try this with let's say 10. Okay, so if we divide these two values, so we can divide this, just flow, okay, this one raster 10 and multiply. So definitely we will use iterations, and so we will use a node called iterator. Okay, so it's called initiator iterator. Duplicate this, rename this one. Let's call this x iter and y iter. Good. So okay, so now we're dividing and multiply, dividing again. The delta x by this value. Okay. Oops. Oh, I'm sorry. Duplicate this. And now we're dividing our y, delta y, with the same amount. Okay. Let's call this x divide and y divide. Okay, so that's a bit trickier, but let's see. For sure we want to all this be done in one frame, so 1 and 1 as well. Okay, so expose the count also. Okay, so let's feed this count with an x divide, and let's feed this count with y divide. Okay, so expose on and connect that. So now we will use a number normalize and multiply this with a delta. Okay, so let's do this more simple. Math and multiply. So I need to connect this by number normalize. Okay, x not x divide, but the delta x. And let's duplicate this. A and value B, number normalize. Okay, so we should do it has to be multiplication. Okay. So if we then further, so I'm at point 3, have a vector, okay, and then we test this all. Let's create the group called tester. Let's call this. This have to be red dots. Oh, whatever. Okay, and we just turn this off. Well, so let's try this. Generator position born pistol shot per call and position. Fingers crossed. Oh. Okay, let's do this. The right group, tester. Good. And the speed is 0. Right. Let's do the lifespan of high value. Okay, so what have we done so far? We have created a two-dimensional array of particles, right? So, and the reason we use this all these divisions and the raster is because of we want these particles to be with the same distance between each other, right? So let's see. X1 is 1, y 1.5. Let's change this. It's 0.5, right? So the distance is the same. Okay. So because of we have used this delta, we have the two-dimensional array, which is starting from 0. So we won't bring this back, and for sure we won't bring this back with the vector, the second one. So easily we can do this. Let's disconnect this. Okay. By the way, I'll try to save this. Oh, yeah, that's good. Let's call the math. Okay. And for sure, if we're adding two vectors, we have the input vector and a second one and the vector also. So this is first one, and the second one is, oh, I'm sorry, spit out the vector. Where's that? Yeah. Okay. Let's try this now. Oh yeah, that's good. So we did the offset for a whole two-dimensional array of particles, and the raster is, which is really interesting. The raster with the raster we can say, oh, well, okay, I need to this be more dense. So let's say 20, right? So this is weird. Why dots? Tester, tester, dots, dots. Oh, this is because of force this setting. Turn this off. Okay, so let's say 50. So whatever value we will be put in here, let's say 3, those particles will be equidistant, right? Okay, so now we have built this array of particles, and then we will examine each and every particle to this process, to whether for whether it is going to eternity or not. So now we want to read all the parameters from each and every point. So all the parameters means alpha, which is an angle, radius, which is the distance, and its initial position. Okay, so let's do this. Oh, the Mandelbrot. Oh. You know, we can even copy that and paste that. So math vector. So let's use the math 0.3 vector y divided by x, y divided, oops, I'm sorry. Okay, y divided by x vector, length, this is good. This argus tangents, so good. So the reason why we didn't copy the memory node is because this is not really a good idea, because it wouldn't work. That's it. So in every dynamic set, you have to use and create its own memory channel, because this will be messed out. Okay, so just create this one again, memory. Okay, spit out the let's initial position. Oh, what's happening? Yep, initial position, radius, and our alpha. So feed this in alpha, radius, and the initial position for this point, which is this vector. Now we have to replicate all the steps to each particle, or not particle, sorry, we just have only the positions but not the particles. So to do that, we can just copy the setup that was done before, right? So let's do this. So just copy that without memory, copy that and paste it. So just recall our memory again, memory. So I'm spitting out initial position, radius, and our alpha. So alpha, radius, radius, and initial position. I believe this. Oh yeah, this step 3. So, and the memory node again. Operator standard memory. Initial position, radius, and alpha. So here's our alpha, radius, and initial position. I believe it is here. Oh no, I'm sorry. We do not write the initial position because the initial position for a whole process is the same. As you can see, it's all the same for each point. It's all the same. So we do not need to write this initial position. Let's remove this from inputs. Okay. So, and of course, our iterations. Let's try this. Copy and paste that. So, oh, it's starting to be complex. What's happening? For each point created in this part of setup, we have to let's say we have to iterate this point with the rotation multiple times. So let's say 10. So when the point is created, we are starting the right side of the setup. So how we do that? Very simple. So like so. So now each point will bring this on. So all that logic will work for each and every point. Okay. So now let's try to create our particles, 2D Mandelbrot particles. Now create, that'll be 2D fractal. That'd be ticks and I don't know, any color. Turn that off. That was a tester, right? Bring back to 0. Trace. So what if it wouldn't be trace, but it wouldn't be on 2D fractal? So the idea of creating these particles, 2D fractal particles, the idea we creating this only after our point is going, let's say, 10 times through the process of we discussed before. So our particle 10 times, four steps, 4 of these steps. It have to do 10 times, and then we create this. So let's use a helper called, that'll be iterations. Should be integer iterations. So 10 times count. So we need to create a particle after 10, after it will do it 10 cycles. So we can use an expression, input scalar A, add input scalar B, add output scalar, that'd be result. So if we connect this, the number yeah. So the number and the iterations, and compare them. So let's say if our number, so this is A plus 1 equals B, then we output 1, else output 0. So A plus 1, this is because our iterator is starting with 0. So if we have the 1 iterations, so this will spit out only 0. But if we compare this, so A should be A is 0 and B is 1, so this this won't be correct. So okay, and the result, let's go here, we turn on our position bar, and the position itself of the particle should be in our initial position, sorry. That should work. Let's try to save this. Trace, let's rename this to D Mandelbrot pistol shot protocol. So let's try this. Something's happening. Okay, so speed and lifespan is a little bit 30. Okay. If you remember, we have 2 types of particles. First type will fly away to the infinity, and the second one will stay near the center in this black area. So let's try to color code them. So okay, import color. Oops, I'm trying to escape. So that the first type will be black. Here's our particle. And the main difference between those two is if our particle going through the process, all this cycle, is reaching the radius of 2, so it becomes, it does not belong to Mandelbrot set, so it flies away, it goes to infinity. So let's try this. Condition standard threshold, let's say 2. 99999. So step 3, our vector So this is a module. We speed out the module. Let's say r is less than 2. So if r is less than 2, so it means that we're staying here. So turn that on. Okay, let's try this. I think it does work, but let's try 30. Okay, let's try 20. Let's try to color code the rest of them. Oh. First math invert. So particle. Let it be red. Good. It does work. So for now, let's try to test this with our tester. Let's do this. That'll be dots. Okay. So as you can see, like we said before, this is our track. Let's try to change it. It's working slow. 20. Let's try to lower the raster. It's 25. Here we go. So, as we said, the red particles are flying to infinity. See? And the black ones are staying inside. So let's bring this back. Display as dicks. Okay. So, as you can see, some particles located at the border needs more iterations to escape. So it tends to go to infinity much slower rather than, let's say, this one. You see? So what if we color code them with a gradient as well, depending on iteration number? So let's do this. Turn this off. Okay. So we need to count how many times this will have radius less than 2. Helpers, math. Oh, it's not a math, it's standard counter. So count 2, count from 0. Okay, so if our radius is less than 2, we're counting. We're adding a 1. So obviously where count 2 is, ooh, where are you? Iterations. Yeah. Okay. So each and every 10 iterations, we have to reset this counter. Reset. So let's see how iterator works. Like it fires off 0, 1, 2, 3, 4, 5, 6. So 10 is from 0 to 9. So if we use an invert, number, invert, go on here, reset. So I believe this is fine. So now we have our count normalized, and we have to color code this. Let's disable this. So I'll use the same viewport color as I used in my setup. Just load this viewport color. Okay, here's our particle. And count normalized. So count normalized will, I'm sorry. So the viewport color from my setup. Okay. So I have to connect count normalize to the viewport color. Let's try this. It definitely doesn't work. What's happening? So I believe I forgot to do this. Count, put this on. Let's try this. Oh yeah, it does work. Let's hide those. So here's our Mandelbrot set. And remove this one also. So can even delete the inner particle. Very standard. Particle die on less than 2. Boolean. Yes. So here's our Mandelbrot setup. Okay, so can fix this by the way, but you can see this border is too much space here. So we need to go into the middle, in the beginning, I'm sorry. So and fix x1, I believe. x1, let's see, 0.8. x2 minus 2.2. And y should be minus 1.4 and 1.4. So with a raster you can dance this. So let's say 50. And with a number of iterations you can raise up the precision. As you can see, those gradients are sharp. So with 40. Oh yeah. So you can play with this is really fun with iterations, or maybe modify something. So here we are, our setup, our Mandelbrot. Okay, I believe some of you find this useful, and good luck, and till next time.